In this lecture, we will discuss the conjugacy in groups and then give some applications of the class equation. So we start by the definition of conjugacy. Conjugacy in G. Two elements A and B are conjugate in G if there exists an element G belonging to G such that A is equal to GB G inverse, or equivalently B is equal to G A G inverse. For example, if the group G is equal to S3, then the elements 1, 2, and 2, 3 are conjugate. So actually here if we choose, if A is equal to 1, 2 and B is equal to 2, 3, then we can choose G is equal to 1, 3. Then G 1, 2, G inverse, that's actually equal to 1, 3, 1, 2, then 1, 3 inverse, this is equal to 2, 3. So therefore the elements 1, 2 and 2, 3 are conjugate in G. Now we state one result here. The relation of conjugacy is an equivalence relation. Now this can be easily proved. So we write a proof here. To show that the relation of conjugacy is an equivalence relation, we have shown that the relation is symmetric, reflexive, as well as transitive. So first we show the relation is reflexive. The relation is reflexive, that is, to show every element A is related to A. And this can be done by writing as we have, that is, since A is equal to E inverse AE, or this can also be written as E inverse, where E is equal to G. So therefore the relation is reflexive. Now second, we can show that the relation is transitive. For this let A be related to B. That is, A is equal to GB inverse for some G belonging to G. Then we need to show that B is equal to some GAG inverse. Then pre-multiplying this equation by G and post-multiplying this equation by pre-multiplying by G inverse and post-multiplying by G, we get, then this gives us G inverse AG. This is equal to B, but this can also be written as, Suppose this is equal to H E H inverse is equal to B, where H is equal to G inverse. So therefore, when A is equal to GB inverse, then B is equal to HH inverse. That means, so this implies B is related to A. So therefore, the relation is also reflexive. This symmetric. Now the third thing that we need to show that the relation is transitive. So for this, let A be related to B.
It's 8 o'clock.
And B is related to C. Then by definition, A is equal to GBG inverse and B is equal to HCH inverse, because A is related to B and B is related to C. Now we need to show that A is related to C. So we have A is equal to GBG inverse. This can also be written as G, but B is equal to HCH inverse. So this HCH inverse into G inverse. Now this is equal to GH, then C, then GH inverse. So this is actually equal to some, suppose G dash C G dash inverse. So this means that A is related to C. So this implies A is related to C. So therefore, thus the relation of conjugacy in a group is an equivalence relation. Now, since we know that every equivalence relation partitions a set into disjoint equivalence classes, so therefore the relation of conjugacy in a group partitions a given group into disjoint equivalence classes. So thus, the relation partitions a group G into equivalence classes. Equivalence class, and each such class is known as a conjugacy class. Thus the conjugacy class for A belonging to G is denoted by C, is denoted by C. Thus CA is equal to GA G inverse such that G belongs to G. So this is the conjugacy class of A. C of A is equal to G, A G inverse such that G belongs to G. For example, if G is equal to S3 and A is equal to 1, 2, then we shall come to the class of 1, 2. Then class of the element 1, 2. This is the set of elements G, 1, 2, G inverse such that G belongs to S3. Then by direct calculations, when we put this G as the different 6 elements of S3, we obtain this is 1, 2, and similarly we get 1, 3, and then 2, 3. For example, if G is chosen to be 1, 2, then G inverse is equal to 1, 2, 1, 2, and 1, 2 inverse, and this is equal to 1, 2. And similarly, if G is equal to the identity element of S3, then again G inverse is equal to 1, 2, and also if G is chosen to be equal to 2, 3, then G inverse is equal to 2, 3, 1, 2, 2, 3 inverse. This can be written as 2, 3, 2, 1, and 2, 3. Then this is equal to 1, 3. And similarly, we will get one of the conjugacy elements as 2, 3. So this is the conjugacy class of the element 1, 2. So once the equivalence class partitions a group into disjoint equivalence classes, and we have denoted each of the classes by C of A. So C of A is a class that contains the element A and elements that are conjugate with A. So this is the class of G that contains A and elements that belong to the class of A. That belong to the class of A. Now, as we have a partition of G into disjoint equivalence class, we can write as we have a partition of G into disjoint equivalence classes. We can write order of G is equal to summation order of class of A, where the sum runs over disjoint classes of A in the group G. Now we proceed towards one more result for proving what should be the order of this class of A. We have that in a form of a theorem. If A belongs to G, then order of class of A is equal to order of G divided by order of normalizer of A. To prove this result, we shall define a 1-1 onto mapping between the two sets G divided by N of A and C of A. So we define a mapping T from G by N of A into C of A by T of G N is equal to G inverse. Then first we show that this mapping is a well-defined mapping. So we show T is well-defined. For this, let Gn is equal to Hn. Then we have H inverse G belongs to N. So this implies, so once we have an element in the normalizer, this N is actually the same short notation for N of A. So this N of A here. So once H inverse G is N of A, this implies H inverse G A H inverse G whole inverse. This is equal to A. So this implies H inverse GA GH is equal to A. Then by some more computations we will get GA G inverse is equal to HA H inverse. So this implies T of Gn is equal to T of Hn. So this means that the mapping T is a well-defined mapping. And now reversing the order of the steps from T of Gn is equal to T of Hn, we will reach back to G of n is Gn is equal to Hn, and that means that the mapping is also a 1-1 mapping. So reversing the steps here, we obtain T is 1-1. And since T is a mapping, onto finite sets, thus T is onto. So therefore, T is a bijection. So once we have a bijection between two sets, this implies that order of G divided by order of N of A is equal to order of the class of A. So therefore, the order of class of A can be obtained by computing the order of the normalizer of A and then taking the order of these two quotients. So we have, with this result, we have one more result here. As we have seen earlier, that order of G is equal to summation order of class of A, where the sum runs over disjoint equivalence classes. Now we can add one more result here for making a little more nice statement for the statement. We have the class of A is equal to a set containing just one element if and only if A belongs to the center of A. And this result can be trivially proved because in this case, class of A is equal to G A G inverse, such that G belongs to G, but when this A is in the center of G, so this is equal to G inverse of A, such that G belongs to the center of G belongs to G. And this is equal to A. So therefore, the class of A just contains one element A if and only if this element A is in the center of G. So now if we combine these two statements that order of G is equal to summation order of C of A and order of C of A is equal to order of G divided by order of N of A, we obtain order of G is equal to order of G divided by order of N of A, where the sum runs over disjoint equivalence class, but this can also be written as this is equal to order of center of G plus summation order of G divided by order of N of A. Now where the sum runs over equivalence classes of elements of G that are not in Z of G. That are not in the center of G. So therefore, we have an equation that order of G is equal to order of center of G plus summation order of G divided by order of N of A, where the sum, or we can simply write A does not belong to the center of G. So we have this equation for the order of group. This equation is known as the class equation. Class equation for G. For example, if G is equal to S3, then the class of A is equal to G inverse such that G belongs to G. So therefore, the class of the identity element is equal to the identity element itself. The class of 1, 2 is the three elements 1, 2, 1, 3, 2, 3, and similarly the class of element 1, 2, 3 is equal to 1, 2, 3 and 3, 2, 1. So this is the partition of the symmetric group S3 into disjoint equivalence classes. Thus, class equation is class equation of S3 is order of G, which is equal to 6, is equal to order of the class of the identity element plus order of class of 1, 2 plus order of class of 1, 2, 3. That is equal to 1 plus 3 plus 2. Or even we can compute the order of the normalizers of identity element, the order of normalizer of 1, 2, and the order of normalizer of 1, 2, 3. And in this case, the order of normalizer of N of A, where A is equal to 1, 2, that is normalizer of the identity element. This will be equal to 6 because identity element commutes with all the other elements. And the order of normalizer of 1, 2 will be equal to 2. And similarly, the order of normalizer of 1, 3, 2 or 1, 2, 3, this is equal to 3. Then using these three values in the class equation, we will obtain that 6 is equal to 1 plus 3 plus 2, and that is the class equation of the group S3.